The emptiness between galaxies holds our universe's deepest secrets. Pioneering explorers venture into this intergalactic unknown, armed with revolutionary tools, to uncover finds that reshape reality itself. By the end of this journey, you will see the cosmos through an entirely new lens. We will reveal how an invisible cosmic web dictates the fate of galaxies, and why the universe's expansion is mysteriously speeding up. These are not just abstract ideas, they are profound discoveries about the fabric of existence and our own origins. What do you believe is waiting for us in the vast, dark silence? For centuries, our Milky Way was thought to be the entire universe, a solitary swirl of stars in an endless, empty night. That profound misconception was shattered by the work of one man, Edwin Hubble. Peering through the powerful lens of the Mount Wilson telescope in the 1920s, Hubble identified individual stars within what was then called the Andromeda Nebula. By measuring the brightness of these stars, he made a staggering calculation. Andromeda was not a nearby cloud of gas within our own galaxy. It was an entirely separate galaxy, millions of light years away. This single revelation tore down the walls of our cosmic prison, revealing a universe filled with countless other islands of stars. We were not the center of creation. We were one citizen among multitudes in a vast, expanding metropolis of galaxies. This was the true dawn of intergalactic exploration. Suddenly, astronomers had a new frontier. Early telescopes, primitive by today's standards, became our first windows into this immense reality. They provided the initial, blurry maps of this new frontier, fundamentally altering our cosmic address. The philosophical shift was as monumental as the scientific one. Humanity was forced to confront its own smallness in a cosmos of unimaginable scale, yet this also ignited an insatiable curiosity. What else was out there in that profound darkness between these stellar cities? This foundational question, born from Hubble's work, is what drives every modern mission and theoretical framework today. It is the direct lineage from those first grainy photographic plates to the advanced space telescopes now probing the deep unknown. Hubble's revelation of a universe teeming with galaxies presented an immediate and profound puzzle. If gravity alone was responsible for holding these vast collections of stars together, their outer edges should rotate slowly, like the distant planets in our solar system. Yet they did not. Observations revealed something baffling. Galaxies were spinning so rapidly that they should have torn themselves apart, flinging stars into the void. The only explanation was that they were held together by a tremendous, unseen gravitational force. A hidden skeleton was providing the cosmic glue. This was our first direct evidence of dark matter. Pioneering astronomer Vera Rubin's meticulous work on galaxy rotation curves provided the critical data. She showed that stars at the outer edges of galaxies moved just as fast as those near the center, a clear violation of the expected laws if only visible matter was present. Something invisible, something that did not emit or absorb light, was exerting a powerful gravitational pull. This mysterious substance, dark matter, forms a vast web-like structure spanning the entire cosmos. Think of it as the fundamental scaffolding of the universe. Just as the steel frame of a skyscraper determines its shape long before the glass walls are installed, this dark matter web dictates where galaxies can form and how they cluster together. We can map its invisible strands through a phenomenon called gravitational lensing. The immense gravity of dark matter bends the very fabric of space-time, warping the light from distant galaxies behind it like a cosmic magnifying glass. This allows us to see the unseen, to trace the outline of the hidden architecture. The scale of this discovery is almost incomprehensible. Dark matter is not a minor component. It makes up roughly 27% of the entire universe, while all the stars, planets, and nebulae we can see account for less than 5%. This means the cosmos we observe is just the glittering decoration on a framework built from a substance we cannot directly detect. It is the ultimate cosmic ghost, a pervasive presence that governs the largest structures in existence yet remains frustratingly out of reach. This profound mystery forces us to question the very nature of reality. What is this invisible component that makes up the majority of matter? Its gravitational influence is undeniable, yet it remains one of the greatest unsolved puzzles in all of science. If an unseen web dictates the fate of galaxies, what other invisible forces are silently shaping the expansion of the universe itself? Just as we came to accept the invisible grip of dark matter, an even more baffling discovery emerged from the depths of space. The universe is not merely expanding, it is accelerating, flying apart at a pace that grows faster with every passing moment. This startling revelation came from teams of astronomers meticulously studying the light of distant supernovae. These exploding stars, acting as cosmic mile markers, revealed that the most far-flung galaxies were receding from us more slowly than our models predicted. The expansion of the cosmos was not slowing down due to gravity, as everyone had assumed. It was speeding up, propelled by a mysterious, repulsive force. Scientists named this enigmatic driver dark energy. It is a fundamental pressure woven into the fabric of empty space itself, a cosmic repulsion that overwhelms gravity on the largest scales. Nobel laureate Saul Perlmutter described the sheer shock of this finding, a result that forced us to rewrite the future of the universe. The scale of this force is almost beyond belief. Dark energy is now understood to constitute about 68% of the entire cosmos, dwarfing even the immense presence of dark matter. Its true nature remains one of the greatest unsolved problems in physics. Is it a permanent property of the vacuum, an energy intrinsic to space itself, or is it evidence of an entirely new kind of dynamic field? This discovery completely upends our cosmic destiny. Instead of a future where gravity might eventually pull everything back together in a big crunch, we now face the prospect of a big freeze. In this scenario, the acceleration continues unabated, driving galaxies apart until the universe becomes a cold, dark, and lonely place, with island universes forever isolated in an ever-growing void. This presents a profound cosmic tug-of-war. On one hand, you have the dark matter web, its immense gravity pulling matter together to form the grand structures of galaxies and clusters. On the other, you have dark energy working to push it all apart, stretching the very space-time that the dark matter scaffold is built upon. How does this relentless push of dark energy interact with the cosmic structures that dark matter has spent billions of years carefully assembling? This cosmic tug-of-war unfolds within a space we once thought was entirely empty. The voids between galaxies are not perfect vacuums. They are filled with an incredibly thin, superheated plasma known as the intergalactic medium, or IgM. For decades, this was a theoretical ghost, an assumed presence that was nearly impossible to detect. The pioneering work of X-ray telescopes like the Chandra Observatory changed everything. By observing the high-energy universe, these instruments have mapped this diffuse material, revealing a cosmic reservoir far richer than anyone expected. This intergalactic medium is not just simple hydrogen and helium, the primordial leftovers from the Big Bang. spectroscopic analysis reveals it is peppered with heavy elements like oxygen, carbon, and iron. These are the ashes of ancient stars forged in nuclear furnaces and then violently expelled by supernova explosions over billions of years. This discovery fundamentally alters our view of galactic isolation. Galaxies are not closed, independent islands. They are dynamic ecosystems constantly exchanging matter and energy with their surroundings. They breathe this cosmic atmosphere, drawing gas in to fuel new generations of stars and expelling enriched material back out through stellar winds and galactic fountains. We can literally see this process in action by studying quasars, the intensely bright cores of distant galaxies. As their brilliant light travels across the universe and passes through filaments of the intergalactic medium, specific wavelengths are absorbed. This creates a unique barcode of dark lines in the quasar's spectrum, a fingerprint that reveals the precise composition, temperature, and density of the invisible material it traveled through. This tenuous plasma is the ultimate galactic lifeblood. It serves as a vast reservoir of raw material for future cosmic construction. A galaxy moving through a dense filament of this medium can accrue gas, sparking waves of new star formation and influencing its very evolution over cosmic time. Understanding the properties of the intergalactic medium helps us explain why some galaxies are still vibrant stellar nurseries while others have grown quiet and red. This interconnectedness, this cosmic recycling system, forces a new question. What are the specific, violent events responsible for seeding this vast expanse with the very elements that make planets and life possible? These heavy elements scattered through the cosmic void point toward a universe of unimaginable violence. One of the most dramatic and mysterious signatures of that violence arrived as a complete surprise to astronomers. In 2007, scientists sifting through old radio telescope data found something impossible to explain. A single, blindingly intense flash of radio energy had erupted from deep space. It lasted for less than the blink of an eye, just a few milliseconds, yet in that instant it released more energy than our Sun emits in 80 years. This was the first detected fast radio burst. Its discovery opened a new window into the most energetic and transient events in the cosmos. Pioneering radio observatories like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, have since turned this curiosity into a field of study, catching hundreds of these fleeting signals. The sheer power of these bursts is staggering. They travel for billions of years, traversing the immense voids between galaxies, only to be captured by our dishes as a brief, sharp chirp. For years, their origins were a complete enigma. How could any natural object produce such a colossal amount of energy and then vanish almost instantly? The leading theories are as fascinating as the mystery itself. Many astronomers point to highly magnetized neutron stars known as magnetars. These are the collapsed, spinning cores of dead stars, possessing magnetic fields so powerful they could erase a credit card from halfway across the solar system. A starquake on such an object, a sudden cracking of its crust, could theoretically unleash a firestorm of radio waves. Other potential culprits include the cataclysmic merger of two neutron stars or matter falling into a newly formed black hole. The most exotic explanations even venture into the realm of speculative technology, though the scientific consensus firmly rests on natural, if extreme, astrophysical processes. A critical breakthrough came with the discovery of repeating fast radio bursts. Unlike the one-off events, these sources flash again and again from the same patch of sky. This repetition allowed astronomers to play a cosmic game of triangulation, using the world's most powerful radio telescopes to pinpoint their home galaxies. They were traced to distant, often unremarkable galaxies, confirming their intergalactic origins, but their true value goes far beyond simply locating them. Each fast radio burst is a brilliant cosmic probe. As its signal races across the universe, it passes through the diffuse clouds of the intergalactic medium, the very plasma we discussed earlier. The burst's radio waves interact with this tenuous material, and by the time the signal reaches us, it carries an encoded message about everything it has traveled through. Scientists can decode this message to measure the exact density of electrons in the space between galaxies and even map the strength of its magnetic fields. It is like using a sudden flash of lightning to illuminate the contours of a vast, dark landscape. These mysterious millisecond flashes remind us that for all our knowledge, the universe is still full of profound surprises. They represent a frontier of the unknown, forcing us to reconsider the limits of physics and the behavior of matter under the most extreme conditions. What other impossibly brief, unimaginably powerful events are flickering in the darkness, waiting to be caught by our telescopes and decoded by our curiosity? The search for their ultimate cause inevitably draws our gaze toward other exotic inhabitants of the cosmic zoo, objects where the laws of physics are pushed to their absolute breaking point. At the core of nearly every galaxy, including our own, lies a gravitational monster of almost inconceivable power. These are supermassive black holes, cosmic anchors with masses millions or even billions of times greater than our Sun. For a long time, they were purely theoretical, but pioneering astronomers like Andrea Ghez and Reinhard Genzel provided the definitive proof. By meticulously tracking the orbits of stars near the center of our Milky Way for decades, they revealed an invisible object with a terrifying gravitational pull, compelling evidence for the black hole we now call Sagittarius A star. The Hubble Space Telescope and other observatories have since found these behemoths at the hearts of distant galaxies, confirming they are a universal feature. This discovery led to a profound realization. Black holes and their host galaxies are not separate entities. They co-evolve, growing together in a complex cosmic dance. The black hole's immense gravity, while confined to a small region, can influence the entire galaxy. It can drive vast winds of gas, heating up the surrounding material and effectively shutting down star formation by robbing it of the cold fuel needed to make new suns. We can witness this violent relationship in spectacular events known as tidal disruption flares. When an unlucky star wanders too close, the black hole's tidal forces stretch and rip it apart in a process called spaghettification. The stellar debris is then devoured, creating a brilliant, temporary flare of radiation that illuminates the galactic center for months. These cosmic feeding frenzies offer us a direct glimpse into the active life of these hidden giants. Their existence pushes our understanding of physics to the absolute limit, warping space and time so severely that our current laws break down at their edge, a boundary known as the event horizon. Beyond their role as local destroyers, these supermassive black holes act as fundamental anchors in the intergalactic landscape. Their gravitational influence can dictate how entire galaxies move and interact with each other, especially during colossal collisions. When two galaxies merge, their central black holes eventually sink to the new core, often forming a binary pair that will one day coalesce in a titanic burst of gravitational waves. This intricate connection forces us to look upward and outward, to wonder if the influence of these dark hearts extends even further, shaping the largest structures in the cosmos. These gravitational monsters at the hearts of galaxies do not exist in peaceful solitude. They are often the final product of a far more spectacular and violent process. Across the cosmos, entire galaxies are locked in a slow, gravitational dance, a billion-year embrace that ends in a profound transformation. Pioneering observations from telescopes like Hubble have captured this process in stunning detail, revealing pairs of galaxies so intertwined they are cannibalizing each other. They are drawn together by their mutual gravity, their spiral arms stretched into vast, luminous streams of stars and gas. These are the tidal tails, the visible scars of a cosmic collision. The antennae galaxies are a perfect example, a pair of spiral galaxies caught in a late stage of merging. Their long, arcing tails, which give them their name, are not made of new stars, but are rivers of existing stars pulled from their home galaxies by immense tidal forces. Within the chaotic central regions, however, something spectacular happens. Clouds of gas and dust violently collide, compressing and triggering ferocious waves of new star formation. These starbursts create millions of brilliant new stars in a relatively short cosmic time, lighting up the merging wreckage. This is galactic cannibalism in its most dramatic form. It is a key mechanism in what astronomers call hierarchical structure formation, the idea that small structures merge to build larger ones. Our own Milky Way is a product of this process, having consumed smaller dwarf galaxies throughout its long history, and it is currently in the process of absorbing others. Computer simulations of these events are not just predictions, they are virtual time machines. They show with remarkable accuracy how the gravitational interplay during a merger funnels vast amounts of gas directly toward the center of the newly forming galaxy. This incoming feast of material does not just make stars, it also fuels the supermassive black hole lurking there. As the black hole gorges on this gas, it can ignite into an incredibly bright quasar, becoming a brilliant beacon visible across the universe. The entire structure of the galaxy is remade in the process. A merger between two spiral galaxies can strip away their delicate disks, leaving behind a featureless, elliptical galaxy. The evidence for this dynamic history is written across the sky in distorted shapes and ethereal bridges of light. Every peculiar galaxy, every ring-shaped anomaly, tells a story of a past encounter. This understanding helps explain the incredible diversity of galaxy types we see today. Why are some galaxies orderly spirals while others are bland, round ellipticals? The answer often lies in their history of interactions and mergers. Their very shapes are a record of violence and assimilation. This dynamic process forces us to look at our own cosmic backyard with new eyes. The serene spiral of the Andromeda Galaxy, our closest major neighbor, is not a static island. It is moving toward us, and in several billion years, the Milky Way and Andromeda will begin their own slow, grand merger. Our galaxy will not exist forever in its current form. It is part of an endless cycle of construction and destruction, a dance of giants choreographed by gravity on the grandest possible stage. If galaxies are constantly colliding and reshaping the cosmic landscape, what does that mean for the stability of the dark matter web that holds them all together? The dance of colliding galaxies highlights a universe of immense structure, but what about the spaces where the music has stopped entirely? Scattered between the brilliant filaments of the cosmic web are staggering emptinesses, regions of space so vast and vacant they defy easy comprehension. These are the cosmic voids, and they constitute the overwhelming majority of the universe's volume. Pioneering surveys mapping the large-scale distribution of galaxies have revealed a cosmos that is fundamentally frothy, a sponge where the glittering galaxies are confined to the thin walls and filaments, leaving behind bubbles of near-nothingness that can stretch for hundreds of millions of light-years. The most famous of these, the Boötes Void, is a spherical region so enormous that if our Milky Way sat at its center, we would have had no knowledge of other galaxies until the 1960s. Its sheer scale presents a profound challenge to our models of how the universe evolved. How could gravity, which pulls matter together, have left behind such an immense desert? The answer lies in the very beginning. These voids are primordial fossils. In the earliest moments of the cosmos, tiny quantum fluctuations were stretched to cosmic proportions by inflation. The regions that were slightly denser than average became the seeds for galaxies and clusters, while the underdense regions expanded into the voids we see today. They are not completely empty, of course. They contain a sparse population of isolated, lonely galaxies and are filled with the same tenuous intergalactic medium that pervades all space, along with the ubiquitous dark matter. But their density is so incredibly low that it has a direct, measurable effect on the fabric of spacetime within them. The expansion of the universe is not uniform. In these underdense regions, where the gravitational pull of matter is weakest, space itself expands faster than it does within the crowded galactic clusters. You can think of the universe as a block of Swiss cheese, where the dense cheese slows expansion, but the empty holes stretch more freely. This makes cosmic voids natural laboratories for testing our theories of gravity and the influence of dark energy. By studying how quickly these voids grow, we can probe the nature of the forces shaping cosmic destiny. They are also dynamic. Voids evolve over billions of years. Galaxies are slowly siphoned away, flowing out along the dark matter filaments that form the void's boundaries, like water draining from a bathtub. This gradual evacuation leaves the voids even emptier with time, making them ever more pure examples of underlying spacetime. To stand within a void would be to experience the ultimate solitude. The night sky would be almost perfectly black, with only a handful of faint, blurred stars representing your entire galaxy, and no other galaxies visible to the naked eye at all. It is the silence between the notes, the negative space, that gives the cosmic web its form. This realization forces a profound shift in perspective. We do not live in a universe of brilliant islands in a dark sea. We live in a universe where the bright structures are the exception, and the overwhelming reality is an immense, expanding emptiness. What strange physics operates in these near-perfect vacuums, and what can their silent growth tell us about the ultimate fate of all we see? The profound silence of the cosmic void is not silent at all. It rings with the echoes of unimaginable violence, vibrations that travel not as light or sound, but as ripples in the very fabric of spacetime. This was the monumental discovery made by the LIGO and Virgo collaborations in 2015. They detected gravitational waves, a prediction from Einstein's theory of general relativity that had waited a century for confirmation. The source was a cosmic cataclysm occurring over 1 billion light-years away, the final, frantic inspiral and merger of two black holes. This was not an observation made with light, but with the geometry of space itself. Imagine dropping a stone into a still pond. The ripples spread outward, warping the surface. Now, replace the pond with the fabric of the universe and the stone with two black holes, each with over 30 times the mass of our Sun, colliding at nearly the speed of light. The resulting spacetime tsunami traveled for eons across the intergalactic medium, passing through galaxies and voids completely unimpeded, until it finally reached Earth, stretching and squeezing our planet by a minuscule amount. LIGO incredibly sensitive lasers measured this infinitesimal distortion, a change in length thousands of times smaller than a proton. This was the first time we truly heard the universe. Each gravitational wave signal is a unique cosmic fingerprint. By analyzing the waveform, the specific pattern of the ripples, scientists can decode the story of the event that created it. They can determine the masses of the colliding objects, their spin rates, and even the distance they traveled. This new window has revealed a hidden population of black holes and neutron stars, objects that had previously been invisible to us because they emit no light. We now know that such cosmic collisions are far more common than we ever suspected. The ability to listen to these events transforms our understanding of the dark, empty spaces between galaxies. They are not passive voids, but dynamic arenas where these invisible, silent dramas constantly unfold. A collision we detect today actually happened billions of years ago, its waves only now reaching us after an epic journey through the expanding cosmos. This raises a tantalizing possibility. What other transient phenomena, what other ripples from exotic objects or primordial events from the birth of the universe are washing over us right now, waiting to be heard? Deep within the cosmic voids and threaded along the dark matter filaments, another layer of the universe hides in plain sight. While our telescopes show us glittering cities of stars, a pioneering search using radio waves has revealed a population of cosmic ghosts. These are dark galaxies, vast structures composed almost entirely of dark matter and raw hydrogen gas, with few or no stars to light them up. They challenge the very definition of what a galaxy is. The first compelling evidence for these phantoms came not from optical telescopes, but from radio observatories tuned to a specific frequency. This is the natural emission line of neutral hydrogen, the most basic element in the universe. When astronomers scan the sky at this frequency, they are essentially mapping the raw fuel for star formation. In vast sky surveys, they began finding clouds of this hydrogen gas that were massive enough to be entire galaxies. Yet when they pointed their optical telescopes at the same coordinates, they saw only profound darkness. There was no stellar light, no spiral arms, just an immense, silent reservoir of primordial gas. One of the most famous examples is a cloud named Hi 122+01. It is a colossal object containing enough hydrogen to form billions of stars, yet it has produced almost none. It simply drifts in the void, a cosmic shipwreck. How can such a thing exist? The leading theory points to the delicate balance required for star birth. For a gas cloud to collapse and form stars, it must be dense enough and cold enough for gravity to overcome internal pressure. A dark galaxy may be too spread out, its gas too turbulent, or it may lack the initial trigger, like a shock wave from a nearby supernova, to begin the process. It is a galactic embryo that never fully developed. Its immense dark matter halo provides the gravitational glue to hold the gas together, but without that critical final step, it remains a shadowy, inert structure. These dark galaxies and isolated hydrogen clouds are not mere curiosities. They are cosmic fossils, preserving conditions similar to those in the very early universe before the first stars ignited. They offer a pristine laboratory to study the initial stages of galaxy formation, free from the complicated pollution of later stellar generations. Their existence forces us to ask a fundamental question. What is the exact recipe, the precise combination of density, temperature, and stability that turns a cloud of gas into a brilliant island of stars? This hidden population suggests that for every luminous galaxy we see, there may be numerous dark counterparts, a silent majority in the intergalactic census. They represent a different evolutionary path, or perhaps a path not taken at all. This discovery fundamentally enriches our understanding of the cosmic ecosystem, revealing a universe filled not just with brilliant stellar cities, but with dark villages and drifting caravans of raw potential. If so much of the universe's structure remains unseen and silent, what other invisible phenomena are we missing, and how do they connect to the most fundamental forces governing reality itself? Deep within the chaotic cores of newborn galaxies, the universe ignited its most brilliant and enduring beacons. These are quasars, the active hearts of distant galaxies where supermassive black holes are engaged in a ferocious feast. Matter, spiraling into the abyss at nearly the speed of light, forms a searingly hot accretion disk that can outshine every star in its host galaxy combined. For a time, astronomers were baffled by these point-like radio sources that seemed to defy classification. The pivotal breakthrough came from pioneer Martin Schmidt. He was studying the light from a quasar known as 3C273, and its spectrum, its unique fingerprint of light, made no sense at all. The familiar patterns of hydrogen were there, but they were shifted so far toward the red end of the spectrum that they were almost unrecognizable. This extreme redshift was the key. It meant the object was not just distant, it was fleeing from us at a tremendous fraction of the speed of light, placing it billions of years into the past. With that single observation, quasars were transformed from curiosities into time machines. They became our most powerful probes of the early universe, their light serving as a message in a bottle from an era when galaxies were young and violently active. The sheer distance of these objects is almost incomprehensible. The light from the most faraway quasars has been traveling for over 13 billion years, meaning we see them as they were when the universe was less than 1 billion years old. They are cosmic lighthouses, and their beams cut across the vast, dark ocean of intergalactic space, but their journey to our telescopes is not a clean one. As this brilliant light travels, it passes through the diffuse clouds of the intergalactic medium, the thin plasma that fills the space between galaxies. Atoms within this medium absorb specific, precise wavelengths from the quasar's light. The result is not a clean, continuous spectrum, but one that is filled with a forest of dark lines. Each of these absorption lines is a clue. It tells us the composition of a specific cloud of gas the light passed through, its temperature, its density, and even its motion. By decoding this forest of lines, astronomers can map the otherwise invisible cosmic web in incredible detail, tracing the filaments of dark matter and gas that span the entire cosmos. This is how we use a single, brilliant point of light to chart the universe's largest structures. The influence of a quasar, however, extends far beyond its role as a beacon. The incredible energy blasting from its core does not just illuminate, it also transforms. These objects can drive powerful winds of superheated gas that rush outward at thousands of kilometers per second. These winds sweep through the host galaxy, violently heating up the cold gas reservoirs that would have otherwise collapsed to form new stars. In this way, a quasar can effectively sterilize its own galaxy, shutting down star formation in a dramatic feedback loop. It is a cosmic self-regulation mechanism where the black hole at the center ultimately limits the growth of the very galaxy that feeds it. This reveals a universe of profound violence in its youth, a time when brilliant, short-lived quasars were far more common. Their discovery showed us that the serene galaxies we see today, like our own Milky Way, likely hosted these incredible engines in their distant past. The supermassive black holes that now slumber quietly at their centers were once the brilliant tyrants that shaped their evolution. What other secrets from the dawn of time are still encoded in the ancient light of these fading beacons? That ancient light from the first quasars carries a message from the very edge of time. But to find the universe's true primordial blueprint, we must look even further back to a time before stars or galaxies even existed. We must look at the birth of the cosmos itself. This blueprint is written across the entire sky in a faint, cold glow known as the cosmic microwave background. It is the afterglow of the Big Bang, the moment when the expanding universe cooled enough for light to finally travel freely, a fossilized snapshot of the universe at just 380,000 years old. For decades after its accidental discovery, this radiation appeared perfectly smooth, a uniform blanket of microwaves, but pioneering missions like the Cosmic Background Explorer or COBE changed everything. Its instruments detected the first whispers of structure, tiny variations in temperature, mere millionths of a degree, that painted a mottled pattern of hot and cold spots across the cosmic canvas. This was the universe's first photograph, and it held a staggering secret. These tiny fluctuations were the imprints of a far more dramatic event, a period of unimaginably rapid expansion in the very first fraction of a second of time, a theory known as cosmic inflation. Think of the universe before inflation as a subatomic speck, a realm of intense quantum chaos where energy fluctuated wildly. Then, in a fleeting moment, it underwent exponential growth, stretching by a factor of trillions upon trillions. This violent stretching did two crucial things. First, it took the entire observable universe and blew it up from a volume smaller than a proton to something much larger than our entire cosmic horizon today, explaining why the universe looks so remarkably uniform in every direction we look. Second, it took those primordial quantum jitters, those tiny fluctuations, and stretched them to cosmic proportions. The denser spots in this early blueprint, revealed as slightly warmer regions in the cosmic microwave background, became the gravitational seeds for everything to come. They were the places where dark matter began to pool, eventually pulling in ordinary matter to form the first galaxies, clusters, and the vast cosmic web. Later missions like WMAP and Planck mapped this pattern with exquisite precision, confirming the predictions of inflation with incredible detail. The specific statistical properties of those hot and cold spots, their size and distribution, are a perfect match for the theory. This means the largest structures we see today, from the great walls of galaxies to the immense cosmic voids, have their direct origins in quantum mechanics operating at the very birth of spacetime. It is a profound connection between the very small and the very large. The cosmic microwave background is therefore more than a relic. It is a direct message from the inflationary epoch, a period of physics so extreme we have yet to fully comprehend it. This primordial blueprint not only explains our past, but also guides our search for the very first structures to emerge from the cosmic dawn. If these subtle temperature variations truly dictated the fate of all matter, what does their specific pattern reveal about the fundamental forces that orchestrated the entire cosmic symphony? Some stars do not live out their lives in peaceful orbits. They are cosmic projectiles flung from their home galaxies at speeds so immense they can never return. These are hypervelocity stars, and their discovery opened a startling new chapter in galactic dynamics. Astronomers first spotted them as strange, solitary points of light moving with impossible velocity across the void. Their speeds can exceed 1.5 million miles per hour, far beyond the escape velocity of even the largest galaxies. How does a star achieve such a breathtaking speed? The most compelling explanation involves a cosmic slingshot anchored by the supermassive black hole at the galactic center. Picture a binary star system, two stars orbiting one another, drifting too close to the gravitational monster. In a violent gravitational dance, one star is captured by the black hole, while the other is whipped around and flung outward at a phenomenal fraction of the speed of light. It is a three-body interaction of unimaginable power, a natural particle accelerator operating on a stellar scale. Galactic collisions provide another ejection mechanism. During the chaotic merger of two galaxies, gravitational interactions can fling stars out like stones from a spinning sling, casting them adrift into the intergalactic darkness. These stellar fugitives become invaluable tools for astronomers. By tracing their paths backward across millions of light years, scientists can reconstruct their points of origin. This reverse engineering provides a unique probe into the gravitational landscape and violent history of their parent galaxies, including the mass and behavior of the central black hole that likely launched them. Perhaps even more surprising is the youth of some of these hypervelocity stars. They are not ancient red giants, but often bright blue and massive stars. This suggests they were born in the dense, turbulent environments near galactic centers and then ejected while they were still cosmically young, their lives cut short from their stellar siblings. As these stars race through the profound emptiness between galaxies, they serve as brilliant candles illuminating the invisible. Their light, analyzed by spectrographs, can reveal the properties of the tenuous intergalactic medium they pass through, much like a lone streetlight cutting through a dense fog. Their ultimate fates are as lonely as their journeys. Some may eventually be captured by another galaxy after billions of years of travel, becoming interstellar immigrants. Most, however, are destined to wander the cosmic voids forever, their light slowly fading as they burn through their fuel in the ultimate isolation. This population of interstellar travelers reveals a galaxy not as a static island, but as a dynamic system that can violently expel its own citizens. It forces us to wonder what other celestial phenomena are born from such extreme gravitational encounters, and how these runaway stars might one day seed the barren voids with new possibilities. Far beyond the reach of any star's light, in the profound cold between galaxies, a population of cosmic orphans drifts in perpetual night. These are rogue planets, worlds untethered from any sun, and they may be one of the most common yet elusive objects in the entire cosmos. Pioneering astronomers using a technique called gravitational microlensing have inferred their staggering numbers. The method relies on a delicate cosmic alignment. When one of these dark, free-floating planets passes directly between Earth and a distant background star, its gravity acts as a tiny lens, bending and focusing the star's light. For a few hours or days, the background star temporarily brightens, revealing the invisible planet's presence before it moves on, and the star returns to its normal brightness. These fleeting events are our only window into this hidden demographic, and the data suggests a shocking reality. Rogue planets could easily outnumber the stars in our galaxy, implying billions, perhaps trillions, of these lonely wanderers exist in the dark. Where do these solitary worlds come from? Many are likely ejected from their home solar systems during the chaotic gravitational pinball of their youth, when interactions with giant planets can fling smaller worlds like ours out into the void. Others might form on their own, condensing directly from small, isolated clouds of gas and dust, never knowing the warmth of a star. Their existence forces us to rethink the very definition of a planet and the stability of planetary systems. Our own solar system may have once contained more planets that were violently evicted in its early history, their orbits destabilized by the migrating giants. The most tantalizing possibility, however, concerns the potential for life. A planet adrift in the deep freeze of intergalactic space seems the most inhospitable place imaginable. Yet if such a world possesses a rocky, insulating crust and a radioactive heart, its internal heat could maintain vast, subsurface oceans of liquid water, shielded from the cold of space. Around a thermal vent on the ocean floor, in perpetual darkness but sustained by planetary warmth, the chemistry of life could potentially begin, completely independent of a sun. This radically expands the habitable zone of the entire universe, moving it from the narrow orbital bands around stars to the interiors of countless dark worlds scattered throughout the void. How many of these orphaned planets are, in fact, frozen arcs carrying secret seas, and what does their sheer abundance tell us about the resilience of life in the cosmos? The discovery of these lonely travelers compels us to look at the empty spaces not as barren, but as a frontier teeming with hidden worlds, each a silent testament to the dynamic and often violent processes that shape planetary destinies. Our galaxy is not merely drifting through a random sea of stars, it is flowing. For decades, astronomers noticed a peculiar motion, a subtle deviation in the paths of countless galaxies, all seemingly pulled toward a mysterious, unseen concentration of mass they called the Great Attractor. The true nature of this cosmic current remained elusive, obscured by the dust of our own galactic plane. The pioneering work of a team using advanced radio telescopes to map the velocities of thousands of galaxies finally unveiled the breathtaking structure we call home. This is the Laniakea Supercluster, a name from Hawaiian meaning immense heaven. It is a vast, gravitationally bound river of galaxies, a single structure spanning over 500 million light-years and containing over 100,000 galaxies, including our own Milky Way, the Andromeda Galaxy, and all our local galactic neighbors. The technique used to map Laniakea is a masterclass in cosmic deduction. Instead of just looking at positions in the sky, astronomers meticulously measured the precise motions of galaxies. They subtracted the uniform expansion of the universe, the Hubble flow, to reveal the subtle, underlying currents caused by local gravity. Imagine standing in a wide, slow-moving river. You can see the main current, but you also feel the tug of smaller eddies and whirlpools around you. By mapping these gravitational eddies and flows, the scientists could trace the watersheds of the cosmos. They identified the boundaries where the flow of galaxies diverges, where one supercluster's gravitational pull ends and another's begins. Within Laniakea, every galaxy is moving along shared pathways, all streaming toward the same gravitational center of mass, the Great Attractor. This region is not a single, monstrous object, but a massive overdensity, a knot in the cosmic web where the pull of dark matter is so strong it dictates the motion of an entire supercluster. Our solar system, our galaxy, and every nearby galaxy are all participants in this grand, slow-motion migration. This redefinition of our cosmic address is profoundly humbling. The Milky Way is not just one city among many. It is a suburb in an immense metropolitan continent, all linked by the invisible threads of gravity. The scale is almost impossible to grasp. If our local solar system were the size of a coffee cup, the Laniakea supercluster would be the size of the entire continent of North America. This interconnectedness highlights the dominant role of dark matter, whose hidden architecture provides the skeleton for this entire structure. Our place within Laniakea provides the ultimate context for local galactic movements, explaining why we are moving toward the Virgo cluster and ultimately toward the Great Attractor itself. It forces us to look beyond our immediate neighborhood and consider the even larger patterns that might be at play. What other immense structures, what even grander superclusters, define the ultimate flow of the cosmos? Even with all the matter we can see and map, the universe still held a glaring accounting error. Cosmologists had a precise prediction for how much ordinary matter, the stuff made of protons and neutrons called baryons, should exist from the afterglow of the Big Bang. Yet when they tallied up all the stars, galaxies, and nebulae, over half of it was simply missing. This was the mystery of the missing baryons, a cosmic case of misplaced inventory that challenged our most fundamental models. Pioneering work using data from the Planck satellite and other observatories finally pinpointed the culprit. The missing matter was not lost. It was hiding in plain sight, scattered throughout the immense voids between galaxies in a form incredibly difficult to detect. This is the warm-hot intergalactic medium, or WHIM, a tenuous, superheated gas that exists in a state between a true plasma and a cool atomic cloud. Its temperature is immense, ranging from hundreds of thousands to millions of degrees. but its density is so fantastically low that a cubic meter of this space contains only a few particles. Trying to see it is like trying to spot a single, faintly glowing light bulb from miles away in a thick fog. So how do you find something so diffuse? Astronomers turn to the most brilliant X-ray sources in the universe. When the light from a distant quasar or a galaxy cluster with a supermassive black hole travels across billions of light years, it passes through these filaments of hot gas. Atoms of oxygen and other heavy elements within the WHIM absorb very specific, high-energy wavelengths of this X-ray light. By analyzing the resulting spectrum, scientists can see the distinct absorption lines, the unique chemical fingerprints that betray the presence and properties of this elusive material. It is an indirect detection, a shadow cast by an almost invisible fog. This discovery resolves one of cosmology's most persistent puzzles, confirming that the universe's ledger of ordinary matter is in fact balanced. These baryons were never truly missing. They were simply hiding in a hard-to-observe state, spread so thin across the cosmic web that their collective signal was almost imperceptible. The implications, however, go far beyond simple accounting. This warm, hot intergalactic medium is a vast cosmic reservoir. It acts as the primary fuel tank for galaxy growth and evolution. As galaxies move through space, they can accrete this gas, pulling it in to form new generations of stars. The WHIM is also the final resting place for material violently ejected from galaxies by supernova explosions and powerful black hole winds, completing a grand cycle of cosmic recycling. Finding these missing baryons deepens our understanding of the universe's composition and energy balance, proving that what we see shining in the darkness is only a small fraction of the whole story. What other subtle, pervasive components of the cosmos are we still overlooking, their quiet presence essential to the machinery of existence? The most violent explosions since the Big Bang itself momentarily outshine every star in their host galaxy. These are gamma-ray bursts, colossal eruptions of high-energy radiation that flash for mere seconds or minutes from the deepest intergalactic darkness. Pioneering satellites like Swift and Fermi act as our rapid response sentinels, detecting these sudden flashes and instantly relaying their coordinates to observatories around the world and in space. This global network then pivots to capture the fading afterglow across the entire electromagnetic spectrum, from radio waves to X-rays. We now understand these cosmic bombs come in two distinct varieties. The long-duration bursts, lasting more than 2 seconds, are the death cries of the most massive stars in the universe. When such a star exhausts its nuclear fuel, its core collapses directly into a black hole, launching ultra-relativistic jets that punch through the outer layers of the star. The interaction of these jets with surrounding material produces the intense burst of gamma rays we observe. The short-duration bursts, lasting less than 2 seconds, have an even more dramatic origin. They are the product of the final inspiral and cataclysmic merger of two neutron stars. The historic event known as GW 170817 provided the definitive proof. For the first time, we not only saw the gamma-ray burst, but also felt the space-time ripples from the neutron-star collision, a perfect marriage of light and gravitational waves. This multi-messenger astronomy opened an entirely new window onto the cosmos. The incredible power of these events makes them brilliant beacons visible clear across the universe. Because we can calculate their intrinsic brightness from the properties of their afterglow, they serve as cosmic mile markers, allowing us to measure vast intergalactic distances with remarkable precision. Each burst's light is a probe. As it travels for billions of years to reach us, it passes through the gaseous filaments of the cosmic web and the halos of intervening galaxies. By analyzing how this light is absorbed, we can take a core sample of the universe's structure, mapping the distribution of matter across cosmic time. These flashes also produce torrents of neutrinos, ghostly particles that rarely interact with matter. Catching a neutrino in tandem with a gamma-ray burst would give us a direct view into the heart of the explosion itself, revealing physics under conditions impossible to recreate on Earth. What do these fleeting, unimaginably powerful events tell us about the chaotic deaths of stars and the birth of black holes in the distant cosmos? The faintest ghosts in the cosmic zoo are not dark galaxies, but something even more perplexing. Scattered throughout galaxy clusters and drifting in the voids are immense, wispy structures as large as the Milky Way, yet containing only 1% of its stars. These are ultra-diffuse galaxies, and their discovery has forced a complete rethinking of what a galaxy can be. Pioneering deep imaging surveys, like those conducted with the Dragonfly telephoto array, were specifically designed to hunt for this extremely low surface brightness light. They revealed a hidden population of these colossal, faint smudges. One of the most famous, Dragonfly 44, is a perfect example. It has the width and the mass of our own galaxy, but its stars are so spread out that it appears almost transparent, a ghostly imprint against the blackness of space. The mystery deepens when we ask how such a fragile object can even exist, especially within the violent, crowded environment of a galaxy cluster. In these dense regions, the gravitational tides from massive neighboring galaxies should have ripped a structure this diffuse to shreds over billions of years. The fact that Dragonfly 44 and others like it have survived means they must be held together by an immense amount of dark matter. Their dark matter halos are exceptionally massive and robust, acting as an invisible shield against disruption. This presents a major challenge to our models of galaxy formation. How does a galaxy accumulate such a vast reservoir of dark matter, yet fail to convert most of its gas into stars? The answer seems to lie in their diverse origins. Some ultra-diffuse galaxies may be failed giants, galaxies that formed in a quiet corner of the cosmos where their gas remained too hot or too stable to collapse efficiently into stars. They are the cosmic equivalent of a field that was never planted. Others are likely the stripped remnants of once normal galaxies. As they orbited through a cluster, their outer stars and gas were peeled away by tidal forces, leaving behind only their dense, star-poor core and its protective dark matter cloak. By studying the subtle motions of their few stars and the faint colors of their stellar populations, astronomers can trace their life history, distinguishing the born diffuse from the ones that were sculpted by violence. These ghostly galaxies are more than just curiosities. They serve as unique natural laboratories for testing theories of dark matter. Their extreme properties push our models to the limit, asking how dark matter behaves on galactic scales and whether its distribution can differ dramatically from one galaxy to the next. Their subtle presence, once we knew how to look, revealed a far wider and more varied galactic bestiary than we ever imagined. If such enormous, ethereal structures can hide in plain sight, what other delicate forms of cosmic architecture are we still missing in the vast, dark canvas of the universe? Our universe may not be a singular, lonely creation. The most profound and speculative frontier in cosmology suggests we exist within a vast multiverse, an endless ocean of cosmic bubbles, each with its own unique version of reality. This radical idea is not pure philosophy, but a natural extension of our most successful theories about the Big Bang, specifically the concept of eternal inflation. In this model, the explosive expansion that jump-started our cosmos never truly stops. Instead, it continues eternally, a runaway process where different regions of space can suddenly slow down and crystallize into their own distinct universes. Our entire observable cosmos, with its hundreds of billions of galaxies, could be just one such region, one bubble in a frothing, infinite sea. Pioneering theoretical work by scientists like Alan Guth and Andre Linde suggests that within this bubbling foam, the fundamental laws of physics are not universal constants. Quantum fluctuations during this process could randomly set the strength of gravity, the mass of an electron, or the number of spatial dimensions differently in each newborn bubble universe. In most of these universes, the constants would be incompatible with the formation of atoms, stars, or life as we know it. We exist in this particular bubble not because it is special, but simply because its unique, finely tuned combination of physical laws allows for our existence. This is known as the anthropic principle, a potential explanation for why our universe appears so perfectly calibrated for life. While we cannot travel to another bubble universe, some researchers point to potential clues etched into our own sky. The detailed patterns in the cosmic microwave background, that ancient afterglow, might contain subtle anomalies like a cold spot that could be the imprint of a collision with another cosmic bubble in the distant past. String theory, a framework attempting to unify all forces, further fuels this concept by predicting a colossal landscape of possible physical laws, with each solution corresponding to a potential universe. The multiverse concept fundamentally challenges the Copernican principle that our place in the cosmos is not privileged. It suggests that far from being the center of everything, our entire universe might be utterly average, one ticket in an infinite cosmic lottery. This pushes the boundaries of science itself, raising a difficult question. If these other universes are permanently beyond our observational reach, can the multiverse ever be a testable scientific theory, or does it reside in the realm of metaphysics? Yet its power to explain the unexplainable, the apparent fine-tuning of our reality, makes it a compelling, if speculative, horizon for human thought. It represents the ultimate limit of exploration, where our instruments cannot yet go, but our minds can dare to wander. If our cosmos is just one branch on an infinite tree of realities, what does that say about the nature of existence itself? Even the void between galaxies is not perfectly empty. It contains a fine cosmic soot, a mist of microscopic grains that subtly dim and redden the light from the most distant quasars. This is intergalactic dust, and its detection was a masterstroke of observational deduction. Pioneers working with data from the Planck satellite and other observatories did not see the dust directly. Instead, they mapped its presence by its faint, cold glow in the far infrared part of the spectrum, a thermal whisper against the cosmic background. Its distribution is not random. These dust maps reveal a ghostly silhouette that perfectly traces the large-scale structure of the cosmic web, clinging to the same filaments of dark matter that host the galaxies themselves. The existence of this dust so far from any stellar forge is a profound puzzle. How did it get there? One compelling theory points to galactic superwinds. When a galaxy experiences a tremendous burst of star formation, the collective fury of supernova explosions can blow colossal winds, ejecting not just gas but also solid dust grains out into the intergalactic medium. It is a form of cosmic pollution on an unimaginable scale. Another, more exotic possibility is that some of this dust forms in situ, right there in the void. Chemical reactions on the surfaces of existing grains in the tenuous plasma could slowly build new complex molecules, a slow-motion alchemy in the dark. This dust is far more than just cosmic decoration. It plays a critical role in the life cycle of matter. These tiny grains act as miniature shields, protecting fragile molecular clouds from the harsh blast of ambient ultraviolet radiation. By absorbing this energy, the dust grains heat up and then re-radiate it, effectively cooling the surrounding gas. This cooling process is essential. It allows the gas to lose energy, collapse under its own gravity, and ultimately form the next generation of stars and planets. In this way, intergalactic dust acts as a catalyst for cosmic construction, a hidden agent that helps transform diffuse matter into the building blocks of future worlds. The specific composition of this dust, rich in carbon and silicates, tells a deeper story about the chemical enrichment of the entire universe. These elements were forged in the hearts of ancient stars and in the violent throes of supernova. Finding them scattered across the cosmic web is direct evidence of a long and dynamic history of galactic feedback, a cycle of creation and expulsion that has been seeding the voids with the raw ingredients for planets and life for billions of years. The next time you look up at a dark, starry night, consider that the space between those brilliant points is not a pure emptiness. It is a reservoir, a chemical archive, and a construction site, all made possible by the presence of an almost invisible dust. Our cosmic address within the Laniakea supercluster may come with a surprising footnote. We could be living in a galactic vacancy, a local underdensity known as the KBC void. This proposed structure, named for the researchers who first identified its signature, suggests the space surrounding our Milky Way for nearly 2 billion light-years is significantly emptier than the cosmic average. It is not a perfect desert like the Boötes void, but rather a vast, bubble-like region where the density of galaxies and galaxy clusters is about 20% lower than expected. This subtle deficit, like a gentle dip in the cosmic terrain, might be skewing our most fundamental measurements of the universe. Pioneers analyzing large-scale galaxy surveys noticed a persistent anomaly. When we measure the universe's current expansion rate, the Hubble constant, using nearby objects like Cepheid variable stars and supernova, we get a different value than when we calculate it from the early universe's conditions imprinted in the cosmic microwave background. This discrepancy is one of the most significant tensions in modern cosmology. The KBC void offers a potential solution. If we are situated in an underdense region, the gravitational landscape around us is different. The collective pull of matter on light from relatively nearby supernova would be weaker, causing them to appear slightly brighter than they should for their redshift, and leading us to overestimate the local expansion rate. Think of it like trying to measure the slope of a hill while standing in a small valley. Your local perspective would be subtly distorted, making the overall incline seem steeper than it truly is. This local underdensity acts as a gravitational lens in reverse, slightly magnifying our view and potentially creating this persistent tension in the data. The debate around the KBC void is fierce, highlighting a central challenge in cosmology. Is this underdensity a real, significant feature, or merely a statistical fluke within the overall frothiness of the cosmic web? Resolving this mystery requires ever more precise three-dimensional maps of the universe's matter distribution, charting the true density of our local neighborhood on the grandest scales. If confirmed, the KBC void would serve as a profound reminder that our viewpoint is not perfectly average. Our entire window onto the cosmos is framed by a specific location, and that location's particular properties could be silently shaping our interpretation of reality itself. What other cosmic truths might we be misreading because of the particular patch of space we call home? The chaos of colliding galaxies does not always end in destruction. Within the vast, shimmering arcs of debris flung into space, new worlds are being born. These are tidal dwarf galaxies, and their observation stands as one of the most elegant discoveries in modern astronomy. Pioneering studies of systems like the antennae galaxies reveal the entire life cycle. As two massive galaxies tear each other apart, their long tidal tails become rivers of liberated gas and stars. This material does not simply dissipate into the void. Under its own gravity, it can fragment and collapse, condensing into glowing, compact knots that are themselves new, bound galaxies. This is cosmic recycling on a breathtaking scale, where the wreckage of a galactic collision becomes the nursery for a new generation. What makes these objects so extraordinary is their unique composition. Unlike the vast majority of galaxies, tidal dwarfs appear to be devoid of dark matter. They are formed from the visible, baryonic material that was stripped from the outer disks of the colliding parents, material that was not deeply embedded within a dark matter halo. This purity makes them perfect natural laboratories. When we study the rotation and behavior of a tidal dwarf galaxy, we are observing the physics of gravity acting on normal matter alone, free from the dominant, confounding influence of dark matter. This provides a clean test for our theories of dynamics and star formation. Their very existence confirms that galaxies can form through a rapid, top-down process, a violent assembly line that operates in mere hundreds of millions of years, a blink of an eye compared to the slow, bottom-up growth of primordial galaxies. These young galaxies are not just temporary features. While many may eventually fall back and be reabsorbed by the larger merger remnant, some achieve a stable orbit and become independent entities, joining the population of small, faint galaxies that populate clusters and groups. They are cosmic phoenixes rising from the ashes of galactic fire. This dynamic birth process illustrates a universe that is not just evolving, but is actively creative. The same violent interactions that can sterilize a galaxy by fueling a quasar can also, in their outer reaches, sow the seeds for new stellar cities. It reveals a cosmos where destruction and creation are two sides of the same coin, forever intertwined in the great dance of gravity. Every galaxy we see is caught in a grand, relentless current, a smooth recession away from us and from every other point in the cosmos. This is the Hubble flow, the primary evidence that the very fabric of space is stretching. Edwin Hubble's pioneering work in the 1920s gave us this monumental find. He was not listening for whispers or looking for shadows, but directly measuring the distances and velocities of other galaxies. His key tool was a special class of stars known as Cepheid variables. These are pulsating stars whose intrinsic brightness is directly linked to their pulsation period. By measuring how long it took a Cepheid to brighten and dim, Hubble could determine its true luminosity. Comparing that to how dim it appeared from Earth gave him a reliable cosmic yardstick, a way to measure distances across the void. What he found was staggering. The farther away a galaxy was, the faster it was receding from us. This relationship, now enshrined as Hubble's law, painted a clear picture of a universe that is not static, but dynamically expanding. This single discovery overturned centuries of assumption and became the bedrock of modern cosmology. It pointed directly backward in time to a moment of incredible density and heat, the concept we now call the Big Bang. The rate of this expansion is quantified by the Hubble constant, a single number that tells us how fast the universe is growing for every million light-years of distance. Pinpointing this number with absolute precision has become one of the great quests in science. We measure it using different cosmic mileposts, from Cepheid variables and supernova in the nearby universe to the faint imprint of the cosmic microwave background from its infancy. Yet a fascinating tension persists. These different methods yield slightly different values, suggesting there might be something subtle we are missing about the nature of dark energy or the properties of neutrinos. On the largest scales, the Hubble flow is remarkably smooth, a testament to the uniformity of cosmic expansion. But if you look closer, you see ripples in this current. The gravitational pull of massive galaxy clusters and the vast dark matter filaments can tug nearby galaxies, causing their motions to deviate from the pure Hubble flow. Our own Milky Way is being pulled toward the great attractor within the Laniakea supercluster, a local motion superimposed on the grand backdrop of universal expansion. Understanding this expansion is not an abstract exercise. It is the key to tracing the entire history of the cosmos, from its fiery origins to its ultimate fate. It forces us to ask what this relentless stretching means for the distant future of all galactic structures and the very particles that hold them together. That faint, cold glow from the cosmic dawn holds another secret. As this ancient light travels for billions of years to reach us, it must pass through the largest structures in the universe, immense galaxy clusters filled with superheated gas. When the photons of the cosmic microwave background radiation encounter the seething cloud of electrons within these clusters, something remarkable happens. The electrons give the photons a tiny boost of energy, a subtle but detectable distortion in the spectrum known as the Sunyaev-Zeldovich Effect. It is as if the primordial whisper of the Big Bang is given a faint, specific echo as it passes through these cosmic metropolises. This phenomenon provided pioneers with a revolutionary new tool. Unlike other methods that rely on the light emitted by a cluster, the Sunyaev-Zeldovich effect works by the cluster's shadow. It creates a specific cold spot in the microwave background that is completely independent of the cluster's distance. This means astronomers can find these massive structures even when they are so far away they are virtually invisible to optical telescopes. The strength of this shadow is a direct measure of the pressure and density of the intracluster gas. This tenuous, multimillion-degree plasma is the true heart of a galaxy cluster, a vast reservoir of ordinary matter that outweighs all the stars in all the cluster's galaxies combined. This gas is heated to such incredible temperatures by the sheer violence of its own formation, the relentless gravitational collapse that built the cluster, and by continuous feedback from supernova and the supermassive black holes at the centers of galaxies. By measuring the Sunyaev-Zeldovich effect, we are essentially taking the temperature and pressure of this cosmic atmosphere. Groundbreaking surveys from instruments like the Planck satellite and the South Pole telescope have used this technique to catalog thousands of previously unknown clusters, building a three-dimensional map of their distribution across cosmic time. This census is vital because the number and mass of clusters at different epochs act as a stringent test for our cosmological models, tracing the growth of the cosmic web itself. The beauty of this method is how it complements other observations. X-ray telescopes see the same hot gas by its brilliant emission, while optical telescopes map the positions of the member galaxies. When all three methods are combined, they provide a consistent and powerful picture, cross-checking each other to reveal the total mass, the gas fraction, and the intricate physics at play within these giant structures. The Sunyaev-Zeldovich effect gives us a direct line of sight into the properties of the most massive bound objects in existence, a clear window into the machinery of gravitational collapse, and the intricate balance of forces that govern the intergalactic medium on its very largest scales. Our galaxy is caught in a vast, silent river flowing toward a gravitational mystery. This is the Great Attractor, a colossal concentration of mass hidden behind the dusty plain of the Milky Way, pulling our entire supercluster and thousands of other galaxies toward a point in the constellation Centaurus. For decades, this was an invisible giant, its presence inferred only by the peculiar motion of galaxies all moving in the same direction against the backdrop of cosmic expansion. Pioneers mapping these galaxy flows noticed something else equally strange. Our motion could not be explained by a pull alone. There had to be a corresponding push from behind, a cosmic emptiness so vast its lack of gravity acts as a repeller. This is the dipole repeller, an immense void whose underdensity gives our local galactic neighborhood a shove away from it. The interplay between these two titans, one an overdensity and the other an underdensity, governs the motion of galaxies across hundreds of millions of light years. The Great Attractor is not a single monstrous object, but the dense gravitational core of our Laniakea supercluster, a knot in the cosmic web where dark matter has pooled to an extreme. Its true nature was obscured by what astronomers call the zone of avoidance, a swath of sky where the gas and dust of our own galaxy's disk block visible light. To peer through this cosmic curtain, scientists turn to infrared telescopes and radio observatories. These instruments can see through the dust, revealing hundreds of previously hidden galaxies congregating in this region, confirming the immense gravitational pull. This mapping of large-scale flows is more than just cosmic cartography. It provides a direct test of our theories of dark matter and dark energy. The fact that such vast currents exist, driven by the gravity of unseen mass and the pressure of empty space, confirms that dark matter provides the scaffolding for these structures while dark energy influences their motion on the grandest scales. By understanding this cosmic tug-of-war, we can better calibrate our cosmic distance ladder and refine our measurements of the universe's expansion. The precise balance between the Great Attractor's pull and the dipole repeller's push helps us weigh the distribution of all mass, both seen and unseen, in our cosmic neighborhood. This grand flow reminds us that our place in the universe is dynamic, a single point in a vast gravitational field where even emptiness has a voice. The brilliant chaos of a supernova does more than just light up the cosmos. It acts as a galactic pump, driving a vital cycle of cosmic renewal. Deep within the disk of a galaxy like our own Milky Way, when a massive star reaches the end of its life and explodes, it does not simply vanish. The blast launches a colossal bubble of superheated gas, rich with newly forged heavy elements like oxygen and iron, out of the galactic plane. This multimillion-degree plasma rises high above the starry disk, ascending into the galaxy's extended halo in a magnificent arc, only to cool, condense, and eventually rain back down in a continuous flow. Pioneering observations have confirmed this beautiful, violent process, naming it the Galactic Fountain. We can witness these fountains in action by studying the light from distant quasars. As that brilliant beacon shines through the halo of an intervening galaxy, its ultraviolet light is absorbed at very specific wavelengths by the falling and rising clouds of gas. This creates a unique absorption signature in the quasar's spectrum, a barcode that reveals the composition, temperature, and velocity of the fountain material. The data shows vast, complex structures of cool and warm gas cycling through the circumgalactic medium, the galaxy's immediate atmosphere. This is not a one-way trip. The gas that was violently ejected eventually loses momentum, cools, and succumbs to the galaxy's gravity, falling back onto the disk in a gentle drizzle or a torrential downpour of raw material. This returning gas is not pristine. It has been enriched, carrying with it the heavy elements cooked in the stellar explosion, the very elements necessary for forming rocky planets and the chemistry of life. This cosmic recycling mechanism acts as a fundamental governor on a galaxy's evolution. By temporarily removing vast reservoirs of gas from the star-forming disk, the fountain effectively puts a brake on runaway star formation, preventing the galaxy from burning through its fuel too quickly. Then, when that same gas cools and returns, it provides the refreshed, metal-enriched fuel for the next generation of stars. This cyclical process creates a dynamic feedback loop, a self-regulating system that helps determine whether a galaxy remains a vibrant blue spiral or slowly transitions into a quiet, reddened system. The influence of these fountains, however, extends far beyond a single galaxy's borders. Some of the fastest-moving material, accelerated by the most powerful supernova, can achieve escape velocity, breaking free of the galaxy's gravitational grasp entirely. This ejected wind, laden with metals, flows out into the true intergalactic medium, seeding the vast voids with the elemental building blocks for future cosmic construction. This continuous exchange of matter illustrates a profound interdependence. A galaxy is not an isolated island, but a dynamic engine in constant dialogue with its environment, breathing in and out over billions of years. The iron in your blood and the calcium in your bones were once part of this magnificent cycle, forged in a stellar furnace and then flung across space by a galactic fountain, eventually finding their way to a newborn planet around a new star. If galaxies are constantly exchanging matter with their surroundings, how does this intricate dance influence the larger architecture of the cosmic web that connects them all? The boundaries of a star system do not end with its outermost planet. Far beyond the familiar orbits, in the cold, dark reaches of interstellar space, lies a vast spherical reservoir of ancient ice. Our own solar system possesses such a structure, the Oort cloud, a shell of frozen remnants from the planetary construction phase. Now, pioneering astronomers are finding compelling evidence that these immense clouds are not unique to us. They are discovering Oort cloud analogues surrounding other stars, ghostly halos of trillions of icy bodies whose presence must be inferred from subtle clues. We cannot see these objects directly, but their gravitational influence betrays them. In distant exoplanetary systems, astronomers observe comets on long, elliptical paths diving toward their host stars. The very existence of these comets implies a distant source, a vast population of icy planetesimals from which they are periodically gravitationally nudged. Similarly, detailed studies of debris disks, the rings of dust and rock around young stars, reveal dynamical structures that can only be explained by the shepherding gravity of an unseen, extended cloud of objects. These clouds are the frozen archives of a system's earliest days. They are the leftover building blocks that never coalesced into planets, cast out to the furthest gravitational reaches by interactions with giant worlds like Jupiter. Each object is a pristine time capsule, holding the original chemical ingredients of its planetary system. The study of these analogues is more than celestial archaeology. It has direct implications for the potential for life. A steady trickle of comets from this cloud into the inner system could be a delivery mechanism for water and organic compounds, seeding barren worlds with the essentials for biology. Yet this process has a violent side. A sudden shower of comets, perhaps triggered by a passing star, could lead to a period of heavy bombardment, sterilizing fledgling biospheres. The ultimate fate of many of these icy bodies is to be completely ejected. In densely packed star clusters where stellar neighbors pass close by, the delicate gravitational grip of a star can be broken. These encounters can strip away a significant portion of the Oort cloud, flinging countless comets on one-way journeys into the deep darkness between the stars. This creates a population of rogue comets, solitary icebergs adrift in the galactic tides, perhaps even ejected into the intergalactic void itself. Realizing that every star is likely the heart of such an immense, invisible sphere fundamentally changes our perspective. It suggests that the space between stars is not entirely empty, but filled with these faint, drifting legacies of planetary birth. How many of these frozen wanderers, cast out from their stellar homes, are now silently crossing the immense gulf between galaxies, carrying within them the raw, unaltered materials of creation. The very first moments of the universe may have forged black holes from pure chaos. These hypothetical objects, known as primordial black holes, are not born from dying stars. Instead, they could have condensed directly from the extreme densities of the Big Bang's birth pangs, in that seething, hot soup of the primordial cosmos. Imagine pockets of space so dense and so turbulent that they collapsed under their own gravity instantly, creating black holes of every conceivable size, from the microscopic to the supermassive. This radical idea, championed by pioneering theorists like Stephen Hawking, offers a potential key to several of cosmology's most stubborn puzzles. For instance, how did supermassive black holes appear so early in the universe's history? They are found in the distant past, at a time when there simply hadn't been enough time for massive stars to form, die, and build up such colossal objects through mergers alone. Primordial black holes provide a ready-made answer. They could have been there from the very beginning, serving as pre-made seeds that grew into the giants we observe at the hearts of galaxies. Furthermore, some of the gravitational wave signals detected by LIGO and Virgo from collisions of surprisingly heavy black holes could be explained if those objects were not stellar remnants but ancient primordial ones. Their unique mass range and distribution might perfectly match the data that otherwise challenges our models. The search for these cosmic relics is a masterclass in indirect detection. Since they would not emit light, astronomers look for their subtle, ghostly effects on the world around them. A population of small, wandering primordial black holes could subtly alter the pattern of the cosmic microwave background radiation, the universe's first light. Their gravity would slightly heat the gas in the early cosmos, leaving a faint but potentially measurable imprint on that primordial afterglow. They could also act as cosmic lenses. If one of these dark objects were to pass directly in front of a distant star, its gravity would briefly bend and magnify the star's light, causing a telltale, short-lived brightening. Astronomers are constantly scanning the sky for these mysterious microlensing events, hoping one will betray the presence of a silent, ancient wanderer. The possibility that these objects could constitute a portion, or even all, of the dark matter is perhaps the most profound implication. It would mean that the invisible glue holding galaxies together is not an exotic new particle, but a vast swarm of ancient black holes, a hidden population drifting through the darkness between stars and galaxies. Their masses could range from less than an asteroid to many times the mass of our Sun, all moving unseen through the voids. Finding definitive proof of primordial black holes would force us to rewrite the first chapter of cosmic history. It would reveal a universe where the most extreme objects were not a late-stage product of stellar life, but a fundamental feature of creation itself, born in the fire of the beginning. What other relics from that first second of existence are still hiding in the vast, dark tapestry of the cosmos, waiting to be found? The primordial whisper of the cosmic microwave background carries more than just the blueprint of the early universe. As this ancient light travels for billions of years, it is subtly reshaped by the very structures it helped to create, a phenomenon known as the integrated Sachs-Wolfe effect. Imagine a photon, a particle of light from the dawn of time, falling into the deep gravitational well of a massive galaxy cluster. It gains energy as it falls in, but as it climbs out on the other side, it finds that the universe has expanded, and the gravitational well has become shallower due to dark energy's relentless push. The photon cannot reclaim all the energy it lost, so it escapes with a net loss, appearing slightly colder to our telescopes. Conversely, a photon traveling through a vast cosmic void experiences the opposite. The underdense region's gravitational potential effectively becomes deeper over time as dark energy dominates, so the photon loses more energy climbing out than it gained falling in, making it appear slightly hotter. These minute temperature shifts, mere millionths of a degree, are not random noise. They are a direct imprint of dark energy's handiwork, a signature of the changing gravitational landscape of the cosmos. Detecting this faint signal required a monumental effort. Pioneering cosmologists performed a precise cosmic cross-reference, comparing all sky maps of the cosmic microwave background from satellites like Planck with three-dimensional maps of millions of galaxies from vast surveys like the Sloan Digital Sky Survey. The statistical correlation they found was unmistakable. The cold spots in the ancient light aligned with the positions of massive clusters, while the hot spots matched the locations of immense voids. This correlation is the fingerprint of the integrated Sachs-Wolfe effect. It is a direct probe of how the gravitational potentials of the largest structures in the universe are evolving over cosmic time. Without dark energy, these potentials would remain relatively static, and this subtle imprint would not exist. Its detection is therefore independent, powerful evidence for the accelerating universe, confirming dark energy's dominant role not through the motion of galaxies, but through the fading echoes of gravity itself. This measurement reveals a universe in a state of dynamic transition, where the very potential energy of space is being fundamentally altered. It forges a direct link between the largest scales, the cosmic web of galaxies, and the most fundamental force shaping our cosmic destiny. If the fabric of spacetime is being stretched so profoundly that it leaves a scar on the universe's first light, what other subtle imprints of this great transformation are waiting to be found? Even the universe's first light holds a strange and unexpected alignment. The cosmic microwave background, that pristine snapshot of infant cosmos, is not perfectly uniform. Its subtle temperature fluctuations, the seeds of all future galaxies, appear to be arranged in a peculiar pattern that seems to defy a foundational rule of cosmology. This is the mystery known as the axis of evil. Pioneers analyzing the exquisitely detailed maps from the WMAP and Planck satellites noticed something unsettling. The hot and cold spots in this ancient radiation are not scattered randomly across the sky. Instead, they show a curious statistical alignment, a preferred direction that spans the entire cosmos. One hemisphere of the sky appears slightly warmer on average than the other, a large-scale asymmetry that should not exist. Furthermore, there is the famous cold spot, a vast, unusually cool region that is far larger and colder than our standard models can easily explain. These are not just minor curiosities, they are anomalies that challenge the cosmological principle, the core assumption that the universe is homogeneous and isotropic, meaning it should look the same in every direction and have no special center or axis. The probability of such features arising in a truly random, isotropic universe is incredibly low, forcing scientists to confront a profound question. Are we seeing the imprint of something fundamental from before the Big Bang, or is our local environment casting a giant shadow? One line of investigation points to local foregrounds. Perhaps the gravitational pull of a nearby supercluster, or even the diffuse haze of our own galactic halo, is subtly contaminating the signal, creating a false alignment from our particular vantage point. Others explore more radical possibilities, like the idea that the universe is not infinite and uniform but has a more complex topology, perhaps even a crystalline structure on scales larger than we can observe. The investigation itself drives a relentless pursuit of clarity. Each new generation of telescopes and data analysis techniques is tasked with peeling away these foreground layers, searching for any systematic error that could explain the axis away. Yet, if the anomaly persists, it points toward new physics beyond our standard lambda-CDM model of the universe. It could be a relic from the inflationary epoch, a scar from a collision with another universe in the multiverse, or evidence that the fundamental constants of nature vary across space. The axis of evil reminds us that our most cherished cosmological models are not infallible truths, but maps that are constantly being refined by the terrain of new evidence. What if the universe is not the same in every direction, and our place within it is not entirely ordinary? Unraveling this cosmic preference could force a rewriting of the universe's first chapter, revealing a beginning far stranger than we ever imagined. That ancient light from the first quasars carries a deeper story, etched into the very absence of certain colors. As we push our observations to the absolute limits, we find quasars so distant their light has been traveling for over 13 billion years, a journey that takes us back to a time when the universe itself underwent a fundamental transformation. This was the Epoch of Reionization, the cosmic dawn when the first stars and galaxies switched on, flooding the cosmos with their harsh, ultraviolet light. For hundreds of millions of years after the Big Bang, the universe was a cold, dark fog of neutral hydrogen gas. Light could not travel far without being absorbed. Then something happened to clear the fog. Pioneering astronomers realized that the most distant quasars held the key to mapping this great transition. By analyzing their absorption spectra, scientists noticed a profound and telling feature known as the Gunn-Peterson trough. In the light of these incredibly ancient quasars, a specific portion of the spectrum, the part corresponding to the Lyman alpha line of hydrogen, was completely black. It was not just a few absorption lines, but a deep, continuous trough. This was the signature of a universe still filled with that pervasive fog of neutral hydrogen. The hydrogen atoms were soaking up that specific wavelength of light all along the quasar's billion light-year path to us. As they looked at quasars a little closer to us from a slightly later cosmic time, that trough began to fill in. The fog was lifting, the neutral hydrogen was being ionized, its electrons stripped away by intense ultraviolet radiation, turning it into a transparent, diffuse plasma. This process did not happen everywhere at once. It was a patchy, gradual cosmic dawn, completed by the time the universe was around 1 billion years old. The very existence of these troughs allows us to pinpoint the epoch of reionization to a crucial window between redshift 6 and 10. This was not an abstract event. It was a dramatic upheaval that forever altered the conditions for galaxy formation. The same radiation that ionized the intergalactic medium also heated it, making it harder for gas to collapse and form new stars in smaller galaxies, effectively setting a lower limit on galaxy size. For decades, the Gunn-Peterson trough was our only clue, a shadow on a graph pointing to this formative era. Now, with the James Webb Space Telescope, we are turning the lights on in that ancient room. We are no longer just inferring the process from a shadow. We are directly imaging the very galaxies responsible for it. Webb's incredible infrared vision is revealing a multitude of small, faint galaxies from this epoch, their collective ultraviolet output more than enough to power the great reionization of the cosmos. They were the cosmic engines that sculpted the transparent universe we inhabit today. Understanding this pivotal epoch completes the timeline from the primordial fireball to the structured cosmic web we see now. It connects the smooth universe imprinted on the cosmic microwave background to the clumpy, galaxy-filled universe we call home. The clearing of that primordial fog was the final act in the universe's early childhood, the moment it became recognizable, setting the stage for everything that was to come. Even before the first starlight flickered, a ghostly sea was already flooding the cosmos. This is the cosmic neutrino background, a relic population of particles born in the first second of the universe's existence. For every proton in the cosmos, there are over 1 billion of these neutrinos, a staggering number that makes them the second most abundant particle in existence after photons of light. They are the universe's oldest surviving witnesses, formed just 1 second after the Big Bang, when the cosmos had cooled enough for these ghosts to decouple from the primordial soup and stream freely across the expanding void. We cannot see or feel this sea, but we know it must be there, its existence etched into the very blueprint of creation. Pioneering cosmologists inferred its presence by meticulously studying the subtle patterns in the cosmic microwave background. The specific way the hot and cold spots are distributed, their size and spacing, is influenced by the total density of radiation in the early universe. That radiation density includes not just photons, but also the immense number of neutrinos that were flooding space, their collective gravity subtly shaping the infant cosmos. This gravitational tug left a distinct fingerprint on the large-scale structure of the universe we see today, affecting how galaxies cluster and how the cosmic web formed. Detecting these specific neutrinos directly, however, is one of the greatest experimental challenges in physics. Unlike the high-energy neutrinos we detect from the Sun or supernova, these relics have been cooled and stretched by the universe's expansion for over 13 billion years. They now possess incredibly low energy, making them all but impossible to catch with current technology. They pass through our planet, our bodies, and our most sensitive detectors without a trace, as if we were trying to hear a whisper in a hurricane. Yet, the scientific pursuit to capture them is relentless. Next-generation experiments are being designed with unprecedented sensitivity, using ultra-pure materials cooled to near absolute zero, hoping to register the infinitesimal bump of a cosmic neutrino interacting with an atomic nucleus. The implications of a direct detection would be revolutionary. It would open a direct window into the universe at 1 second old, a time far earlier than the cosmic microwave background can show us. We could measure the exact number of neutrino species and probe their properties, testing the very limits of the standard model of particle physics. This relic sea connects the infinitesimally small world of quantum particles to the grand architecture of the cosmos, revealing how the tiniest building blocks shaped the largest structures. What other secrets from the first second of time are still flowing through us, completely unseen? Our journey through the cosmic vastness reveals a universe built from shadows and whispers. The foundational discoveries of pioneering explorers have completely rewritten our cosmic story. We now know that the glittering galaxies are mere decorations on a hidden scaffold of dark matter, a cosmic glue that dictates the architecture of everything. We have measured the relentless push of dark energy, a force that ensures the cosmos will expand into an ever colder, darker future. These are not minor details. They are the dominant realities of our existence, proving that most of the universe is made of substances we cannot see and do not yet understand. The fleeting brilliance of gamma-ray bursts and the silent drift of rogue planets remind us that the cosmos is in constant, violent motion, a dynamic arena where entire worlds are cast adrift and stars are flung into the void. Our understanding comes not from direct sight but from brilliant inference. We map the invisible web by watching how it bends the light of distant quasars. We hear the collisions of black holes by sensing the faintest ripples in spacetime. We find the missing atoms of the universe by reading their shadowy fingerprints in the light of the brightest beacons. This is the essence of modern exploration. It is a testament to human curiosity and technological ingenuity, a process of piecing together the grandest puzzle from indirect clues and subtle signals. Each mystery solved, from the nature of the great attractor to the birth of tidal dwarf galaxies, adds a new thread to a richer, more complex tapestry. We are left with a profound sense of our place. We are temporary residents of a small planet, orbiting an average star in a quiet suburb of an immense supercluster, all caught in a cosmic flow we are only beginning to chart. This perspective is not meant to diminish us but to liberate our wonder. The night sky is no longer a static curtain of lights. It is a living, breathing, and deeply mysterious entity, filled with invisible forces and silent, drifting worlds. Let this journey be an invitation to keep looking up, to keep questioning, and to support the telescopes and missions that are our eyes and ears on the universe. The greatest discoveries are not behind us. They are waiting in the profound darkness just beyond the edge of our current understanding, beckoning the next generation of pioneers. We would love to hear which cosmic mystery captivates you the most. Share your thoughts in the comments below and subscribe to join us on our next deep dive into the cosmos.